All right, I have that it's noon. So, welcome to the Barn of Tomorrow webinar series. This series highlights emerging ideas, technologies, and management practices that are shaping the future of livestock production. So, thank you for joining us for this conversation. Today, we're joined by Dr. Brett Ramirez, who is going to be talking about big data and livestock ventilation. So, we're excited to have Brett kick us off on this journey and excited to have you here with us. If you have questions during the webinar, please feel free to type them into the chat box. If you'd like to ask your question using voice, at the end of the webinar, we'll open that up so that you can ask Brett the question. But if you have a question at any time, type it in the chat and we'll make sure to address it. So with that, thanks, Brett, for joining us today, and the floor is yours.
Awesome. Thank you, Dan. So yeah, I'd also like to extend my welcome to everybody taking their time to join us today. I think we're all here because we want to get a better understanding, and I think we all understand that there's an opportunity out there with the amount of data that we're collecting in some of these barns to maybe do some more interesting and valuable, and valuable solutions to some of our common problems. So today it's going to be a little philosophical to some extent, mainly kind of on that more conversation side of things. Won't be getting too deep into the data, but I kind of want to provide a good kind of overview of what goes into understanding big data, right? And it's not just on the data side, there's also the physical system side, the sensors, and everything that goes into collecting that. So I'm an associate professor in the Department of Agricultural and Biosystems Engineering here at Iowa State University. And we are going to go ahead and get started. So I thought this would be a good slide to start things off. So I was in China last year and had an opportunity to visit this farm. And this is really what, when I think about big data, the amount of data that this farm was collecting was just enormous. I mean, every type of sensor, and we'll talk about all the different varieties, but just an incredible amount of data. And, really the question is, what do you do with it? You can collect all sorts of things 24/7, 365 days a year, and really just generate enormous, enormous amounts of information. I think then it comes to, well, what do you do with it? I think there's still a lot of things that we don't know that maybe data can answer those questions. But some of it, we just need to have a better understanding of the pig, the environment in general, before we start trying to measure things that we don't actually fully understand what it means. Take for example air quality, right? We can measure carbon dioxide. We understand that it might have some negative effects, but we don't really know at a deep scientific level of what is, the production loss for every 1,000 ppm of carbon dioxide over say 5,000, right? So there's still some of that fundamental information that we just don't have a good understanding on. And so when we get into all these measurements and all this data, we always have to remember that we don't know what we don't know and keep that in mind. So with that, also, I take maybe a little bit different approach. I go into a lot of barns and I see a lot of different technologies in barns. And I've come to kind of the conclusion that it doesn't matter how expensive, high tech, this is for controllers, but you could extend it to other pieces of technology. If the settings are wrong, it could lead to a bad environment or excessive energy usage. The human has to program the controller or the technology. The human has to start it. And if that human doesn't start it correctly or get the right settings, it's never going to do what you want it to do well. Another thing I run into a lot is if the controller doesn't work, the controller cannot control if the equipment doesn't work, the controller cannot control the environment. So we have to have everything else in the barn fully functional so that the technology can do its job and use the equipment or whatever it is to perform that task, right? So everything has to work. Too many barns, there's too many pieces of equipment that are not working, and therefore we can't control the environment. Poor designs, improper sizing, all those things cannot be fixed with technology. And you're going to see an effect on the environment or the energy usage. We have to do maintenance, right? And maintenance is a human thing, right? It's technology can't maintain some of our equipment. It might help, notify for maintenance, but it can't do the work. And then I'll get into this a little bit later. If the sensors aren't accurate, they're not in the right spot, we're not going to have any really good information to use at the end of the day. We often try to use controllers or technology to try to troubleshoot or try to find a solution, but we really need to understand what that challenge really is and what the solutions are. This is one example. You know, Controllers operating, that the alarm's been tripped for a missing sensor. It's gone, for 4 days, right? So that's 4 days of, not no temperature feedback for the controller to do its function. And somebody has to actually go out there and fix that temperature sensor. It broke, maybe the wire snapped, a pig ate it. But again, when we see stuff like this, a notification that these more advanced controllers can do, the human still has to act on it, right? And so as we get into it, like, notifications are great, but they don't solve problems, right? Somebody has to actually act on that problem. And anymore today, I mean, everybody gets so many notifications across so many different information platforms. It's getting that notification and then acting on it is how we actually get to a real life solution. Kind of going back to one of my earlier points, these are just common problems across, pig barns. I mainly do pigs and layers. Technology in any way or data cannot solve any of these issues, right? I mean, these are all problems that are going to require a human at some point to go in and either make the repairs, improve designs, maintenance, whatever it is, right? All these different things that occur that we see in barns every day. Does not matter how much data there is. We're still not going to get a good environment if we have the simple things incorrect. So what led us to the ability to collect big data is if we go back 20, 30 years, some of the original controllers, were very simple stage controllers, just used temperature as a feedback, controlled some relays. And that's what they did. And they did a good job at maintaining a good environment inside the barn. With the increase in computing power, we've now been able to get controllers that are essentially little mini computers that can now perform many, many different tasks, a lot of different inputs and outputs that essentially can go into a space where now we can start to look at that information. So here's an example of some of what we call like a smart controller today that has this ability to generate that type of big data. So when we look at the added values of these different controllers is we have so much more flexibility to control ventilation different ways. We have more options on staging, influences, over under amp alarms. So if we're looking at motors, so then we can preemptively try to get there and get that solution, that repair done quicker. We're preventing more hardware failures. We can finally get descriptions that might actually provide more information on what's going wrong with the alarm versus just a generic controller alarm, temperature high. Right now we can dig into it, we can see, we can plot, and we have a lot more settings that can limit potential negative action. So what I mean there is, there's a lot of different things and the weather changes a lot. So we have a lot more control on adjusting certain settings to kind of minimize, big swings in temperature or, minimizing the dynamics of whatever the outside weather does or equipment does. We can remote log into these. It saves a ton of time on travel if I can just go online, look at what the controller is doing, save that initial cost of going to that barn to see if it's able to be diagnosed remotely. So when we look at the current state of controllers, we have many different brands. We have stage control to kind of a more smart machine learning, adaptive based. Then we also have hardwired and wireless, right? There's a growing push into the diagonal. So there's many different companies out there that have a lot of different features. But this is kind of one representation of how, traditionally we're a stage control with hardwire. And there's kind of more systems are integrating wireless sensors or adaptive features that can control and make decisions a little bit different than that traditional staged approach. Oh, so what can we do today? I'm going to skip that. I'm not sure how that slide got there. Oh, and that one too. Sorry about that. So what we can do today is we have many different options for measuring things, right? So we can break it down into infectious diseases, welfare, production, and go through all these different ways of measuring. So we can put wearables, kind of depends on the species. We have different imaging, sound, thermal, VOCs. We can measure temperature, humidity, airspeed, carbon dioxide, uh, methane, ammonia, and just tons and tons of different sources of data. And I think the next webinar series is going to cover kind of more specifically how we do that. I'll keep it a little more high level in this discussion. So when we get all this data, there's data generation, and then it's got to be delivered and stored somewhere. We have to pre-process that data, get it organized in a usable form. Then we're going to run some machine learning validation, select that best model, do more analysis, find out that report, and then eventually make that decision. So I'll kind of go through that with some case studies here at the end. So when we make a measurement, most assume that it'll be good enough. So we really have to think about, as we make these measurements, are they really that accurate? Do I need a variety to actually understand it? So when can I get away with, a sensor here, a sensor there, or do I really need to look at everything holistically? We also have to understand, is the measurement we're making working correctly? How accurate is it? How critical is it? In that process, right? So when we make a measurement, and again, being on the ventilation side, we can use temperature, for example, on a simple temperature sensor, right? We have that mechanism. That signal has to be conditioned, processed, transmitted, displayed, and then it ends up as information. So anywhere in this process, any small errors or challenges is going to have a negative effect on how that data is used and how it's interpreted. So one of the sayings is garbage in, garbage out, um, which basically means, if you put bad or inaccurate or unreliable data into a model, you are not going to get a good usable information. Most likely the model will still work. It probably will still train and it will still be validated and it'll have a really nice high R-squared with a low root mean square error. But that doesn't mean that the information is good, right? Models can work on all sorts of data. We have to have good information going in to have good information coming out. Then we look at barn environments. It's a wet, dusty, corrosive, highly variable, changes quite dynamically. And we have to keep that in mind as we're generating that data and then trying to make those subsequent decisions from it. And where do you put sensors in a barn, right? It's highly variable, especially as we build larger and larger barns. We're getting more and more stratification throughout that space. And what does it look like? Here's just examples of sensors. We have different equipment companies that all link up to the controllers. We have a lot more wireless options now today. We have cloud analytics and all tied in with management. So there's a wealth of data, right? There's so many different sources, so many examples, so many platforms. There's kind of minimal, cross-platform connections, and there's just so many different ways that one can generate that data and all the different sources. So it makes it a little bit challenging to truly look at things, together. So if you wanted to tie in production with environment, with feed and whatever else, it does get a little bit challenging to kind of make all those connections and really start looking at it from a big data perspective. On the climate side, so I'm more of my passion. We don't tend to use the climate data, temperature, humidity, air speeds, gas concentrations inside the barn, and we don't really do a good job at combining them to really understand what the impact is on pigs, broilers, cattle, layers, whatever it is. And so I think we still have a lot of opportunity to work together to combine all these different sources so we can start to kind of figure out some of these interactions and what that best environment is for the animal. So I'm going to switch gears a little bit and talk a little bit more on how do we approach these problems. So we have, artificial intelligence is pretty common phrase anymore today. And this kind of shows the subset of you have deep learning. Inside of that is machine learning, and then that's fully encompassed by artificial intelligence. So AI, is performing those tasks that are going to typically require a human. And so it takes a long time to develop these models. It's very computationally heavy, hard to interpret how it actually works at the end of the day, and then the accuracy can vary. Right? I'm sure we're all familiar with how inaccurate some of the AI tools are in generating content. Then with machine learning, it's going to be an algorithm that learns from the data patterns, and then it's going to make those decisions, whether it's a classification or a pattern, and it's going to figure out, kind of what to do based off that. Not as hard to create, and kind of varies on the complexity of how much computational power. We have a much better understanding of how these models work, and we can get some pretty good accuracy with it as well. Then you get into deep learning where there's just all these just thousands and thousands of these layers of neural networks that make this very complex model with the big data. Is going to be very long lead time, computational heavy, and it's also very black box. So we really don't understand fully what goes on in those models, as the complexity is so high, so it makes it challenging. So why and when do you use machine learning? And so this is kind of the general framework. Um, when it's hard to get a solution by hand, you know, and we need something that maybe a physical model can't be represented in normal physics and science, can be better than humans, and it can handle just so much more data than what our normal processes do. So with machine learning, you have to get training data. You're going to create an algorithm. There's the learning period, which is going to then generate a trained model, which then has results, or you can feed new data back into the trained model to keep making those decisions. So how does machine learning relate to statistics? Statistics is where, we're going to draw these conclusions from what we're analyzing. And it has a very high interpretability because we understand the stats models, and it's founded, versus machine learning is going to be more on predictive scalability and autonomy. So kind of training and letting that model do its own work. And there's just a little bit less of the understanding of how that works. So now I'll talk quickly about a case study. Um, so we studied 5 wean to finish barns in West Central Iowa, just using temperature sensors and water meter. We also had some relative humidity. We logged the data kind of at irregular time intervals, anywhere from 1 to 15 minutes, which is what they call sparse logging, which is pretty common approach to save on space. So if the value doesn't change over a period, there's no need to log that value over and over again, just to save on storage space of all that data. So here we were mainly looking at water patterns, and some of the other patterns related to the environment. So what we did here is, what the goal here is to kind of figure out time scale and how do you best analyze some of this data, because it's not simple in a traditional sense of how to get that information. So my grad student Felipe used many different models, trying to understand what is the best representation of this data, and how do we analyze it in time series with different chunks of time, to kind of make that eventual decision. So in the general framework for this is we were using a forecasting model. We went anywhere from 24 to 168 hours, predicting up to 2 hours. And so we are trying to figure out is, can you predict that water usage and detect anomalies in that water usage inside the barn. So that was the kind of the main goal. So we're trying to classify things as normal or an anomaly. So if it's deviating from what we would expect. So this is kind of some of the animations of that water usage, showing the variability and when those changes occur throughout the day. So what ended up for the results, we have different training windows. Really the goal is to find the correct size. So as you're doing that predictive modeling, trying to figure out where the anomaly's at, and whether it's in water, temperature, health, caused by health, wherever that's at, is, understanding that window is critical to being able to make that prediction of an anomaly if it does occur. So we ended up using about 3 to 4 days. So one example, just kind of to show what goes into creating these models and analyzing this data and really, the time, because this was months of work of, statistics and programming that goes into analyzing this information and then coming up with useful models that could potentially work in the future. So another one we were looking at is kind of same barns with different ventilation styles. One was a power natural. The other was a power tunnel barn, also in West Central Iowa. Um, Same measurement system to record temperature, humidity, and water usage. And so here we were looking at, could we detect a difference in the environment between the two ventilation styles based off of, temperature, humidity index, um, and the water usage. And so what this kind of revealed, and it makes sense, we observed that on some of the very hot days that, water usage decreased during the middle of the days when the temperature was the warmest in the early to late afternoon. And basically, essentially, as the pigs get hot, they're going to reduce their feed intake and subsequently their water intake. And so this pattern emerged on hot days. And so what we're looking at is trying to classify as, these days of potential heat stress based on these two peaks versus a cold day, which is only going to have one peak, right? So the pigs are going to be consuming feed throughout that entire day. So you see a much more steady water usage pattern throughout that day. And that's what we call, a one peak day, which is cold or thermal neutral conditions. And then we wanted to figure out is how many instances of these single peaks and double peak days occurred throughout the summertime. So this is the algorithm my grad student Felipe created, trying to using essentially z-scores on the data for each period, and then applying a filter to kind of detect when do those peaks occur, and how many there are. This is very observationally very easy to do as a human. Clearly you can see there's one peak during the day, and on the hot days there is two, right? It's very clear from visually looking at it. However, trying to get statistics and training an algorithm and filtering this information to detect these peaks is much, much, much more difficult. So spend a lot of time trying to get that algorithm, as you have little dips and changes and, other, different things that are happening in the barn that are going to cause somewhat inconsistent, um, parameters. It gets very challenging. So ended up using a moving window or lag on how much of that historical data is fed into the period, and then set the deviations, and try to minimize the false positives. So what we found is the tunnel ventilated farms had combined p-value of 0.001 and natural was 0.975. And we saw quite a big difference between the number of one peak days and two peak days as cold and thermal neutral and hot between the different ones. So this is showing the peaks compared to the temperature humidity index for both the tunnel and the natural rooms. So then if we look at the number of peak frequencies, so how often do you see those peaks? We see much lower instances of those peaks during the middle of the day for both the barns, and a little bit more tailored towards the evening in the tunnel barn versus the natural barn, probably most likely just due to having a consistent, tunnel airspeed over those pigs. So another example is diagnosing different ventilation settings, based on this data. So this was data from a controller that shows the number of heaters and fans running, and then your outside temperature, and then the average temperature inside the room. So this is a warm day, so temperatures in Fahrenheit. For those of you that are in Celsius, warm day, about 33, I believe, kind of showing, how that staging works and, how that system then staged down into the evening. And so really there's not much to look here. at, but is one of those things when we start to have challenges or we need to start troubleshooting, being able to plot this data and look at it, and then being able to superimpose different equipment and sensor values is important for getting the whole picture of what's going on. So this one was an example of figuring out that the heaters were turning on very soon after um, the minimum ventilation fans were ramping up. So we call this the yo-yo effect. Um, and it results in a large waste of propane because after the heater runs and the fan turns on because the offset's too tight, all the money spent in propane is exhausted out through those fans. And so by taking a quick plot of heaters and fans running versus temperature, you quickly can see the inverse effect of heaters are on, fans on, and staging up the system every time after those heaters were running. And so this was a quick fix. We increased that offset from when the heater turned on below the set point, and resulted in saving money for the producer. And then with a little bit more data, you can start to understand the spatial variability of the different conditions inside of the barn. So again, this mainly just from a visual perspective, but one can use it to kind of start diagnosing and understanding if we have too much stratification and what the solution is. But it takes a lot of sensors to do this. So it's a lot harder when there's only about anywhere from 4 to 5 sensors in a barn typically. This was much more than that, but again, you can see this is a cage-free aviary, different barns during different conditions to kind of understand how does this barn ventilate and if there needs to be changes in the future. And so you can see the fans, all the air moves right to left, or sorry, left to right. And you see at the different levels or heights inside the room, different patterns of stratification occur. And so for this, we ended up having to add stir fans in this barn to help mix some of that air to kind of help minimize that stratification across the barn. So what can you do next? I think really it's critical to understand the limitations of sensor values and the just limitations of data in general. Why it sounds great and there's so many opportunities, we still have to remember the physical system and where that information comes from. That physical system is critical. We have to understand the interaction of different components and remind ourselves that the fundamentals are important, right? One could, if you plot temperature and humidity outside every day, they're inversely related, and one could say that, they're inversely correlated. However, there's physics behind that and psychrometrics that explains why the temperature and humidity behave that way, and it's not really something we need to look at from a model perspective. It's based in physics. So we want to keep that in mind. Then we have to think about what questions do we ask? How do I, improve my performance, reduce utility costs? What can I use all this ventilation data for? Whether it's, predicting a potential disease outbreak or out of feed event. There's many different things one can do. It's just, they're simple questions with very challenging solutions just due to the complexity and just the general biology of animals. And how they behave on a daily basis. I think one of the critical things is always visualize it. It's hard to look at spreadsheets and numbers. If we can get it into a graphical form, it's a lot easier to see patterns before we start getting into the more computationally heavy modeling. And then you just got to start digging into it. There's a lot of great resources out there and different ways to learn, but that's kind of how you approach it is different across depending on your questions. So with that, I will take any questions. I really appreciate everybody taking their time today. I look forward to hearing your thoughts.
Thanks, Brett. So if anyone does have questions, please do put them in the chat. Otherwise, can I get you to stop sharing? And I'm going to do my advertisement for next week as we get questions hopefully rolling in. So next time, Han Wook is going to join us, and he will be talking about livestock sensing technologies. So potentially some of those wearables that Brett mentioned. so that we can collect some other data. And then, I went too quickly, it didn't move from that slide. So you will be able to find this webinar, and if you miss any in the future, on our YouTube channel, youtube.com at Barn of Tomorrow. And we are sharing presentation slides. So you can see the link to the presentation slides. So if you're looking for any of those, they will be available. The slides should be available now, and the YouTube video will come available in a day or two. So with that, if you have questions for Brett, now is the time. Oh, and we have one, so I don't get to ask the first one. So, Brett, is there a specific type and or R value of insulation used in Iowa compared to other locations for swine and poultry? They were wondering the role of insulation and essentially how it impacts utility cost or stability of temperatures.
Yeah. So the so yeah, the R value is going to be different based on climate. We insulate here due to the cold weather, but as you move into the warmer climates, you also need insulation as well. However, with a lot of barns are at such high air exchange rates anymore, that the insulation may not have as much as a effect. Um, but yes, I do think insulation type and level is going to have an impact on the utilities. It might not be much, but there will be some impact. I know, here for walls, we typically use bat insulation with loose fill fiberglass in the ceilings, and that changes all over the world. There's some barns today with structurally insulated panels, for example, which is a rigid styrofoam type insulation. It just kind of varies depending on where you're at in the world.
Perfect. And then I have a question for you on sensor placement and data quality. Uh, you showed some slides about how variable a barn can be. You have done a fair amount of work on sort of that stratification and variability. What are some of your best tips about thinking about, let's just say, temperature sensors in a barn? How do I make sure I'm getting useful data, and what are some of the things I should look out for?
Yeah, so you always need at least two temperature sensors because in case one fails, the controller still needs one for feedback. And then kind of after that, it gets a little challenging, right? There's a cost benefit ratio on how many sensors you need to really to control an environment, and it really just depends on barn size at the end of the day. I don't know if there's a good rule of thumb of temperature sensor every 60 feet or so, and then in each direction, but generally that's somewhere what we cover. Um, like a 60 by 60 square is a pretty common number. Good or bad, I don't know. I don't know if we for a controller standpoint, I'm not sure if we need much more information on that. But when you get into some of these really large, 200 by 500 foot barns, they're going to have upwards of maybe 16 temperature sensors, just because there's so much airspace inside, that building.
Mhm. And then one of the things you alluded to was maybe as we move forward, there's a chance to use forecasting or maybe some upcoming temperature models to sort of adjust where our ventilation systems might be. I think of this as when it gets really cold in the winter, I start turning my heat up a little bit to be prepared. What's the future of that, or what are we doing in control systems right now to help us out with that on the barn side?
Yeah, I think there's maybe only one system out there that does have that, by using the forecast for the day does increase its ventilation rate earlier than waiting to respond to the temperature change inside the barn. Otherwise, it's not super common. There's not many that do that, right? You need an internet connection, um, and access to a weather API to get that data. But yeah, there are some out there doing that has the ability to get ventilation at a higher stage earlier, knowing that it's going to be a very hot heat stress potential day.
Mhm. And then you mentioned visualization, and that sounds both easy and hard. Certainly, the first thing we want to do is make a graph and look at something so that we can understand it. What are some of the best practices you've found in order to do that? I mean, your yo-yo example where we were turning on heaters right after fans ran is really useful. But how do I make that happen quickly enough that I can diagnose barn problems?
Yeah, that's a good question. And that's where when you go back to that whole process, it's challenging. Not all controllers are friendly in the sense of how they generate and store that data. Most have built-in graphing functionality, but it's limited to certain variables, or it's hard to quite get it to line up in the scale correctly. But best practices is really, start small, start with, a few variables and keep adding to it and trying to make sure that that graph doesn't get too busy, overcrowded, because that can happen in a hurry. So I start small. I mean, hopefully the data is accessible, plottable, in a timely fashion, but otherwise it might take some time to post process and get it into that usable graphical form.
Perfect. Thanks, Brett. And then we have another question on CO2 versus oxygen. Is the number of times the livestock have used the air, or is that related to disease spread? How do you think about air quality and sort of ventilation and disease spread for livestock?
Um, Yeah, I think ventilation plays a role, right? There's, aerosol virus particles in the atmosphere that float around, and I think concentration of livestock has a huge impact on it, right? As we put a lot of animals on the sites, at least here in Iowa, we're increasing, some transmission by exhausting it at high rates, but it also dilutes it. Um, so there's a lot, I think, different factors that go into it.
All right, now you're going to get pounded with questions since everyone's sending questions all at once right now. All right, so your next one was have you had any experience with or seen systems that are using thermal imaging cameras to collect data and utilize it somehow for controls?
The only one I saw was in China. That one robot thing took thermal images, and they were using it for fever detection and just kind of general information on the pig. But that's about the only one I know of. Otherwise, I use it for finding leakage in barns.
Hmm. And you've done some work with heat mats versus zone heating for
Yep.
piglets, and you're not using it for control, but it lets you on the research side sort of see what's happening. Is that fair?
Yep.
Yeah. All right. And then your next question is going to be if 16 temperature probes, does the controller average them? Can an alarm be established for each? What should I be doing with all that data to make a ventilation decision?
So probably with that many, they'll have them zoned. So they'll have, certain quadrants, for example, on their own sets of actuators. So they'll take the average of the zone for each one of those.
Okay. Pork productions moved to total slats in the 90s, simpler controllers. How much has modern controllers improved pig performance versus the 90s model of housing? And how much of it is other stuff like genetics or feeding improvements?
I'd say it's probably genetics and nutrition and health. Those three are probably the main ones for performance. I'm sure housing has had an effect. I would be very interested on how one could quantify that. Um, Otherwise, I would say, I didn't have a slide in it, but I have one that the shows, we still control ventilation essentially the same way. I mean, it's still a stage system that uses temperature feedback. I know there's some that are a little bit more advanced than that, but for the most part, it's still a pretty much the same control logic from, a TC5 to an edge. It's essentially similar. There's just a lot of other features in the edge. And I think really the biggest thing is the peace of mind for the grower or producer to be able to look at that information remotely, to be able to check on that barn, without being there. But otherwise, that's a great question.
So, in regards to that question, I'm going to push you on a follow-up. You showed some data on a tunnel ventilated barn versus a naturally ventilated barn and their water consumption pattern in the day. And maybe there was less heat stress in that tunnel ventilated barn or signs of heat stress. Yeah.
Yeah.
So, could you comment on how that may or may not translate to performance improvement?
Potentially, I mean, right. Heat stress decreases feed intake, which decreases, body weight gain or longer time to market. So yeah, there could be an impact on that. So, I mean, I think, um, mainly in some of the more tropical, humid climates, you're starting to see much more shift from natural to tunnel. So I think there is quite a bit of improvement. I just saw some data from a group in Guatemala that has shown just remarkable increases in productivity, just from switching from natural to tunnel. So I think there is quite a bit to gain there if you're going from natural to tunnel. Now, if you're going, tunnel with something else, the improvements might be a little bit more marginal.
Mhm. And then the last one, maybe $1 million question for you. Is there a dollar value in big data to be passed on to the growers for those in vertically integrated systems? Or how are we going to make these systems pay for themselves and be a better manager?
I don't think there is one right now. I think it's tough. It's a very tough sell at this point, for what that is. I mean, until something becomes more automated in analyzing the data, then I think you can pass down a value. So um, there's not really a system there's one out there that I can think of that interprets it and then provides an informed, uh, use that term loosely, a suggestion on what to do about that environment. So there might be some if there's very obvious things that are happening inside the barn environment that are causing, maybe sickness, heat stress, whatever, and the producer actually has the ability to do something. So if there's a little bit more information in terms of like you need to go, figure out why is your temperature spiking, 10 degrees above ambient every day, something like that. And then I think there is value there. We haven't gotten quite there yet.
All right, so last chance for questions. But in the meantime, I'm going to ask Brett to give us his last word. But what are some things on this big data with ventilation that you're excited for, innovations that you see on the forefront, and maybe where are we going from here in this realm of livestock production?
I think it's kind of what I just had on there of, a system that's analyzing everything and then providing tailored recommendations on what to do. So interpreting everything and understanding how the barn has performed and how it should perform given a current state, and then being able to actually inform the grower or producer of what they actually need to do or
Mhm.
not to do or whatever. That's what I think is pretty cool.
That sounds great. So with that, thank you everyone for joining us. Hopefully we'll see you again next time. Oh, and I got one more question, right? As I said that, in your experience, a farmer is able to manage a big amount of environmental data or needs to be managed by someone else who's really handling this.
Ooh, that's another tough one. It kind of depends on scale, right? So, a large vertically integrated system is going to be probably have to do it themselves to some extent because they have just so much information and they have to keep that in house. For the individual producer, it's probably manageable. If they have just one barn, it's possible. But generally, in a larger system, you might need some additional expertise that's non-traditional to what a typical vertically integrated company would commonly have in their expertise for their employees. So there might need to be some additional, um, skill sets that a larger company might need to have. And I think, can give data to anyone, right? But it takes understanding the system to really make something useful from it. So I think, even with having data people in a large company, they still need to understand the system and what the limitations of that data are.
Perfect. Thanks so much, Brett, for kicking off our webinar series. And to everyone who joined us today, thanks for tuning in. Hopefully, we'll see you again on a future episode.
Yes.
Th-
Thanks, Dan. Have a
Thanks,
good
Brett.